So we were working on Chapter 10 in quantum mechanics, and we had gotten done describing sort of all the different four quantum numbers, and we talked about how that leads to different shapes for the electron orbitals. The thing we want to kind of transition into next is taking a look at the energy of the levels. And we can go back to that Bohr model. So see, you know, if I draw an s orbital, that kind of can be the Bohr model. That really is an s orbital for using the Schrodinger ones. And it's just always easier to draw the s ones. But realize I could draw a p orbital in there or a d orbital in there and have the same thing. And we said that it takes a different amount of energy to remove an electron. For instance, if I wanted to move an electron from the first shell versus the second shell, which one do you think is going to be easier to remove? Yeah, why? Kind of. There's part of that. Yeah, electrons and the nucleus. Well, actually, we shouldn't say the nucleus. It's technically only the protons. That's an attractive force, right? Therefore, the closer the electron is, the more energy it takes to remove. Therefore, it's harder to remove from n equals 1 than, say, n equals 2. And so, if we take a look at it, for when we're looking at the chemistry, a lot of the chemistry we've always talked about involves the electrons. For instance, when we make a sodium plus 1 ion and a chlorine minus 1 ion, there's an exchange of an electron between those two atoms. And where is that electron coming? Well, we're going to find that it comes from the electrons in the outermost orbitals, or the electrons that are the furthest away from the nucleus. Jess?
Is it supposed to be closer the electron is to the nucleus?
Yes, the closer the electron is, the more energy it takes to remove. Therefore, it's just showing that there's an interaction between them. Put whatever you want. Remember, it's your words to describe what I'm saying. My words mean nothing. I put my words up there mostly to slow myself down, because otherwise I talk too fast. I tried doing PowerPoints one year. Holy crap, I could finish an entire chapter in a day. I don't think anyone understood anything, and no one had time to let that information sink into their head, but I can talk really, really fast when I want. So again, put these things into your own words. Have them make sense to you before, worrying about exactly what words I use. And make your own spelling mistakes. No, I'm not even going to worry about spelling errors. So if I take this sort of, 3D picture, because that's not 3 dimensions, right? It's only 2 dimensions on a piece of paper. What I can do is make an energy level diagram that looks like this, where this is simply energy. And there really is no x-axis. It's just where we're going to list the orbitals. And so what we can say is that the 1s orbital has the lowest amount of energy. And if we go higher in energy, then we're going to find that we have our 2s. And what else do we have if we have the second set of quantum numbers? We have a 2p orbital, right? And how many 2p orbitals were there? Do you guys remember? There's 3 of them. So remember, the number part in like 1s simply means that's the n. This is simply the L quantum number, or the shape. And then what we're going to do is we're going to represent by these dashes. So like, for instance, how many of these there are, that's how many orbitals there are. So we've got all 3 quantum numbers kind of represented here, right? So I've got the 1s, 2s, 2p. And so what that's saying is that on that diagram up there, there really is another orbital, and we can draw our 2p orbital. And then if we go one more shell out, I can of course have my 3s orbital. I can have 3p orbitals. And what do I get when I have my third quantum number? Yeah, I can now have d orbitals. And how many d orbitals are there? Yeah, because there's 5 different orientations that we can draw a d orbital for. So when we're putting electrons around an atom, what we're going to do is we're going to fill in the bottom part of the chart first. So for instance, if I was taking a look at hydrogen, I'd have a simple, just 1 electron right there. Does that make sense? And you know, if I wanted to talk about helium, I'd have to put another electron. And notice that, you know, one is got m sub s plus a half, and one has n sub s minus a half. So, you know, we've got that notation. We've got those 4 quantum numbers. And what we're doing is we're just saying there's a lot of different ways that we can draw or to think about those quantum numbers. And which way we think about it is sort of, whichever way is sort of easiest to draw or honestly requires the least amount of work. Now, the other idea I want you to keep back in your head is that these are all probabilities, right? Meaning the electron can really be in a wide range of spaces. So for instance, if I look here and I look at the probability and I look at the distance from the nucleus, one of the things that's weird about quantum mechanics is you can have things like this, where here's my 1s orbital. And so when I draw a 1s orbital, and I drew a big one, so we'll just go with it, you know, n equals 1, I draw it as a simple dotted line, right? But remember, there's a probability the electron is a little bit closer. There's a probability that that electron is also a little bit further away. And so then if I try to sketch a 2s orbital, we find it's kind of interesting. It actually has a little bit of probability that it's closer. It has almost no probability that the electron is as close as in the 1s orbital area, and then it has its peak further out. So here's a sort of a 2s orbital. Now where the peak occurs is sort of where we think about, you know, drawing our 2s orbital. So here's my n equals 2 orbital. And so remember, we're dealing with these probabilities, and so yeah, we do have shapes. I mean, we really, you know, the probability distribution really does look like a dumbbell, but we can almost think about it, I like to say, it's kind of like a fuzzy dumbbell. And so that leads to some interesting behavior for some of this. And the thing that really kind of complicates matters is that so what we can think about is we know that the protons are attracted to the electrons, or that the electrons are attracted to the nucleus, right? What other force should be occurring in an atom? For instance, if I draw something like this, you know, here's an electron, here's an electron. They're both attracted to the nucleus, but what about between the electrons? Yeah, there's a repulsive, oops, I wanted to switch to red. So between the electrons, there's a repulsive force. This leads to the fact that the outer electrons are even easier than expected. To remove, because they're being shielded from the inner electrons. So basically, inner electrons shield outer electrons. And electrons in the same orbital tend to not shield each other, tend to do not interact. Because an electron in a 2s orbital, well, if I have another electron on the very far side of that 2s orbital, those two electrons are so far apart, they've got the nucleus between them, that they don't tend to interact. So electrons in inner shells and outer shells interact with each other. Electrons in the same shell don't interact with each other. What this leads to is a shifting in the energy levels. And so that energy level diagram I drew shifts and it changes. And so what happens is we sort of get we should every student take a stenography class to learn to write quickly. A valuable skill in life. How many people did high school speech and debate? That's where I learned to write really fast, because you had to write down what the other person was saying so you'd remember it to respond to them. And I don't know, did you guys do debate or did you do like extemporaneous speeches?
My class is called debate, but first we started out with speeches and then we got to debate.
Did you do like Lincoln Douglas or policy debate style? Or do you have no clue what I'm talking about? That's okay. So what happens to our energy levels then is they start separating. So, you know, the 1s is still the lowest. The 2s is still the next lowest, but the 2p goes upward in the energy level. So because of all the electrons in those 2p orbitals, because the 2p orbital is slightly larger than the 2s orbital, it goes up in energy. And then we've got our 3s, and then our 3p's are shifted up. And here's where it gets a little complicated, and this is what leads to a little bit of the funkiness in that periodic table shape. We should have the 3d electrons higher in energy, but it turns out that in between those, we actually sandwich that 4s level. And so the 4s level is actually in between the 3p and the 3d. And so if you correspond that to the shape of our periodic table, oops, like this. So remember, what did the rows in the periodic table represent? This was just n equals 1, right? N equals 2. Oops, this should be too wide, I guess, if we're really drawing it better. Then we have n equals 3. And we have n equals 4. Oops, that top one shouldn't. These two should be like that. There we go. And so, for instance, we said that this represents our 1s's, right? Then I've got these two represent 2s. And then there's my 2p, 3s, 3p, 4s. Then we had our 3d, 4p in there. So notice that the d's lag by 1. So the d orbitals tend to lag by 1. And of course, then what that's going to do is that causes the f orbitals to lag by 2 quantum numbers. And so the idea is that, notice, elements show up in the 4s column before they show up in the 3d column. So that energy level splitting is what's partially responsible for the shape of the periodic table. I mean, the majority of the shape is simply s orbitals can hold 2 electrons, p orbitals hold 6, d orbitals hold 10, and f orbitals hold 14. But the reason the d orbitals kind of shift down one row in the periodic table is because of that splitting of the energy levels due to the electron-electron shielding. And so we don't have to understand any of the math behind the quantum mechanics that does that. We have to understand the outcomes of it. Haley, did you have a question?
Does that say lag?
Yeah, they lag by 1, meaning the numbering is 1 less. So notice we go 4s, then we go back to the 3d. And notice that the 3d really should be up here if we thought about the energy levels as all being equal, but because of that shifting of the energy levels, because they start mixing and getting a little bit out of order, it kind of lags by 1 quantum number. Does that kind of make sense? Okay. There's one other trick to remember this. So I personally prefer to remember it based on the shape of the periodic table. Mostly because guess what you're given on the test? Periodic table. The other way that you can remember the energy levels is you can make a little chart like this. Oops, that's an F. 5s, 5p. What does what? What? What's an F orbital? That's the two blocks that are down at the very bottom. So this is where our F orbitals are, down here. We don't usually get to them very often, so kind of, I don't know, sometimes I feel like we should just erase them from the periodic table and not worry about it some days, but they're there, so we'll mention them. We won't make any molecules with them. We won't do much with them, but they're there. So the other way to realize which level is the lowest is you can do this diagonal method. So it goes 1s, 2s. So the 1s is less than the 2s. And I'm going to skip putting in the little less than signs just because it's annoying. Then I've got my 2p, 3s. Oops, 3s. I've got my 3p, 4s. So see, that's where that's sort of out of order, right? Then I go 3d, 4p, 5s. And then I do my 5d, 5p. And of course that continues on. So this is our lowest energy, which really means it requires the most energy to pull the electron away. And this would be considered the highest energy, because it takes energy to put the electron up in that high of an orbital. It takes less energy to remove the electron from the element. And so the way energy is normally thought of is it's thought of as a well. And so when we say the lowest amount of energy, that also requires the most amount of effort to take it out of a well, for instance. Yeah. So the bucket that's lowest in the well is going to take the most effort to pull it up. So it's kind of confusing, but that's generally the way that energy is thought of in chemistry. It's sort of, it's a little bit counterintuitive sometimes. Now we're not going to worry about it too much because we're not going to talk about energy that much. My other class gets all sorts of fun stuff. Okay, so we're building our periodic table. We're looking at where the electrons are. We've got a couple rules that we need to have to explain where all the electrons are. These are sometimes called the Aufbau principles. And then some of the principles in the Aufbau principles have other names. For instance, the first Aufbau principle is also called the Pauli exclusion principle, and we've already seen that one. Principle. He basically said that no two electrons can have the same 4 quantum numbers. And then we also have the second and third rules, and these are sometimes also referred to as Hund's rules. And basically the first one says that we always fill from the lowest to highest energy. Actually, we need to add a fourth one in there. I should point out that the number of rules varies depending upon books. Some books will say there's 4 rules, some will say there's 3, some will say that like the second rule that I wrote is part of someone else's rule. As far as I can tell, it's confusing and different in every book. So if you read a different answer in another book and you put that down on a test, as long as it's reasonable, I'm pretty happy. Jess? What's this chapter all about? Quantum numbers. QN is quantum numbers. So we always fill from the lowest to the highest energy. What? Hunds. H-U-N-D-S. So we always fill from the lowest to the highest energy levels. If we have what are called degenerate energy levels, and that would mean things like D or P and D orbitals for us. We're not going to do too many F's. meaning they have orbitals that have the same energy, then electrons go into different orbitals, meaning don't pair up electrons until you have to. And we'll show this in in an actual example here in a minute. We'll go through the first, say, 5 or 6 elements in the periodic table. And then the other thing that it says is that electrons in degenerate energy levels have the same spin, meaning the same m sub s number. What it's really saying is that electrons are going to stay as far apart as possible. I mean, if we put this sort of in layman's terms, it's basically saying electrons stay as far apart as possible for as long as possible. And the part about the having the same m sub s numbers, that really gets into more mathematics, but realize that if they have the same m sub s number, they interact less than if they would have different m sub s numbers. So what we're going to do now is we're going to start building the periodic table. And one of the things that we're also going to look at is different ways to do this notation. So we're going to have, for each element, sort of a different way to write it. Okay, so we're going to have electron configurations. That goes like 1s, 2, 2s, 2, etc. Where again, we already know that the first quantum number is n equals 1. Or the n number. The second quantum number is talking about L, or the shape of an orbital. And then the little part at the top is the number of electrons in the orbital. So an s orbital can have 2 electrons. So you can have 1s2, but it's impossible to have, say, 1s3. Doesn't exist. There's no, you can't put 3 electrons in an s orbital. The other way that people tend to do this is with box diagrams. And sometimes they actually use boxes. I tend to use just lines because I'm too lazy to draw the full box. So for instance, we would have our 1s orbital and our 2s orbital, and then we represent the spin of the electrons as up and down arrows. So, the 1s still has the same meaning. It's the n quantum number. The s means it's an L. And then the up and down arrows represent the n sub s quantum number. So whether we're writing 1s2, 2s2, or drawing little box diagrams, doesn't matter. Preferentially, now on the test both of them will be there, but preferentially we'll generally write electron configurations. In this class, we don't care if the electrons are up or down. We don't go into the more complicated theories where it matters if the spins are aligned or not aligned, so we don't have to worry about any of that. That's, well, you count them. There's 2, right? There's 2 arrows, so there's 2 electrons. Each arrow represents 1 electron. So for hydrogen, we can simply say it's 1s1, or if you're writing it kind of in a box diagram, and I said I don't draw boxes, I usually just draw lines to represent the orbitals, you can just simply say it looks like that. So hydrogen's nice and easy. And then helium has 2 electrons. That's also pretty easy. That's 1s2, or we have 2 electrons. And then what we note is that the spins are opposite when we put them in that orbital that's together. Right. If the arrow is pointing up, we generally say that it's m sub s is plus a half. The arrow is pointing down, we say m sub s is minus a half. Now, technically, we can't tell whether an arrow should be pointing up or down, meaning it's perfectly legitimate to also draw the arrow pointing down, because we can't tell whether m sub s is plus or minus a half when we just are writing electron configurations. It really can be both. I generally draw them up by default just because that's how I draw my arrows. No, because I'm too lazy to put the other half. meaning it doesn't matter. So you thought I was writing upside down ones? And then we can write lithium like this.
Where are you getting this from?
What do you mean where?
Like,
So like the one in the, so what is, so those are describing those orbitals, right? So that's going back to, for instance, we said a 1s orbital is spherical, right? And then down here in lithium, what we're saying is that we've got a spherical orbital, and then there's a second spherical orbital. And so this represents our 1s orbital, that represents our 2s.
how do you know that there's that many?
Electrons?
Like
with
1s,
the
2,
elements.
2s, 1, yeah. Like, where do you get that?
Okay, so how many electrons does hydrogen have? So I can only have one electron. How many electrons does helium have? 2. Lithium has 3. So that's where I'm getting those numbers from. It's simply the number of electrons that the element has, right? And then how do I know that I first fill the 1s orbital and then the 2s orbital? That's those energy level diagrams. So remember when we kind of drew this diagram, or you have to learn it from the periodic table, or you have to use this little trick here to kind of think about how to draw that diagram. And so what we're doing is we're simply starting from the lowest energy and putting electrons in, and eventually, you know, you're putting electrons in the 5p orbitals because you filled up all the lower energy levels. So yeah, every number is coming from someplace specific, and it is a little complicated because it's a lot of new nomenclature. It really is honestly like learning a new language. This is the language of quantum mechanics. So what's the next element after lithium? It's beryllium, right? 1s2, 2s2, or we have... I understand that you guys need to digest. That's why we tape the lectures. You can go back and watch the lectures and digest to your heart's content. But I do have a certain amount of material I have to get through each day in order to meet the state requirements for finishing the class. So
Are those V's or arrows?
those are arrows. Well, you guys are really picky.
So, like, will their electrons always add up to be the atomic number?
They need to
'Cause
write under the arrows there when
You can write 1s, 2s if you want, but it's also implied that you know whether you're talking about 1s's or 2s's or things like that. So, what's after beryllium? Boron. So, I've got 1s2, 2s2, and now I can start using 2p orbitals, so I've got 2p1. So if I'm drawing my orbital diagrams, you know, I've got 1s, 2s, those are all my 2p orbitals. I've filled up all these inner ones, and I've only got one electron in that 2p orbital. I think these are all in your book too. Meaning I don't know if they put the entire periodic table in your book. Did anyone actually read your book? When's the last time you read the book? Out of curiosity, anyone? So yeah, read the book. I mean, seriously, all this is in there, and then you can kind of digest it definitely at your own pace. I mean, realistically, we should actually assign the reading before we talk about it, but we know that doesn't really work. So carbon has 1s2, 2s2, 2p2, because it's got 6 electrons. And here's where things start to get a little interesting, at least. According to the Hund's rules, we have to put those electrons in different orbitals. Oh, those are ugly-looking orbitals. So we have it in 2 different orbitals. The reason is the orbitals keep the electrons as far apart as possible. So the idea is that, you know, if I've got a bunch of p orbitals, if I put an electron in this orbital, then the farthest away I can put one in another orbital is in a separate one, not in the exact same orbital. Because they'd occupy the same region of space if they were in the same orbital. But if they're in different orbitals, they occupy different regions of space. So electrons want to stay as far apart as possible. They don't pair up until they have to. And then the other part is that those spins are always aligned, meaning both of them are going to be up or both of them are going to be down. They're not going to be one up and one down. So we yes. Then we pair them up as late as possible. So nitrogen is 1s2, 2s2, 2p3. We're only going to do the first row of the periodic table, so don't worry too much. Yes. But the whole point is there's a pattern, right? And if you can learn the pattern, then you don't have to memorize any of them. Otherwise, yes, you will have to memorize all 110 elements because any single element could be on the test. So this is kind of like learning your multiplication tables, right, Jess? You got your multiplication tables down? Nope. Are you typing them on your phone? You're just sitting there? You're so dead looking. Oh, you're studying biology, I see.
Can you explain again when those 3 point up instead of go down?
Because according to Hund's rules, they have to have the same, they have to be spin aligned is what it's called, meaning they're all either spin up or all either spin down. Now, the real reasoning behind that, you have to look into the mathematics of the quantum numbers and realize that the lowest energy is if they're aligned as opposed to unaligned. There's no real good explanation that I can give you for a physical reason behind it. Turns out that there's less interaction between the electrons if they have the same spin than if they're flipped.
Or why they're not going in the same way 1s and 2s?
Well, remember, in the 1s and 2s, they have to have different quantum numbers, right? So when we pair them up, they have to have opposite quantum numbers. So if we kind of looked at this, that would be, like if we listed the 4 quantum numbers, that would be 1, 0, 0, a half. And the other one in that orbital is 1, 0, 0, minus a half. And so we kind of pair them up when we have to, but that's the last resort. They would rather be unpaired. And same, so that the reason we keep them in 3 different orbitals is that way they're not paired, right? And then the spin aligned part, again, that you just...
Each one of those 3 that point up have half of minus half?
Correct. So if we looked at the quantum numbers for those 3 electrons, they're in the second orbital, they're in a p orbital, and they're either going to have 0, minus 1, or plus 1 for that quantum number, and then the other quantum number is always going to be plus a half. So what they differ in is that third quantum number, or the orientation of the orbital, meaning whether they're in this orientation, or that orientation of the orbital.
Does the book talk about the pattern at all?
Oh, yes. Like I said, there's 3 ways to remember that. There's 2 ways to, well, actually, there's 3 ways to memorize the pattern. You can either look at the periodic table and remember one or 2 little things. You can build that little diagram and do the diagonal lines. Or the third one is literally, I guess you could rote memorize the order. It's not impossible to do. I got better things to do with my brain than memorize it. I sort of just picture the periodic table when I'm doing all of these things. So what's after nitrogen?
So when you run out of 2, you going into 3C?
Not 3C,
Yes.
3S. So here we actually have to pair up one set in the p orbitals. And one of the things that you're going to start to notice, and maybe we can even point it out here, what charge does nitrogen normally have? Yeah, nitrogen is normally a -3. So I'll put this in a different color because we're kind of doing this a little in advance. Well, notice that how many electrons does it want to fill up all its orbitals? 3. What charge does oxygen normally have? So how many electrons does it need to have to fill up its orbitals? So one of the things we're going to learn is the charges on the atoms are directly related to filling up their orbitals. So let's do two more elements. We've got
We have to,
we have to what?
I just don't remember the arrows like that. Like I'm doing the arrow part.
I mean, maybe your teacher drew them like this
No, he did the half.
or like that.
We did the half ones, but I don't remember. We did a whole different like diagram type thing with it.
Did you have boxes instead? Did he draw it in little boxes like this? I'm just too lazy to draw the whole box. That's why I just draw lines.
Maybe.
Oh, so
I don't know.
the charge shows the amount of unpaired?
Not unpaired, but the amount of electrons that it wants to in order to get to completely filled orbitals. I guess technically maybe that's the amount of unpaired electrons too. I don't know. We haven't looked at
Because looking
cations
at the
yet.
drawing, the nitrogen has 1, 2, 3, 4, 5, 6, 7 electrons,
Yeah,
and 3 of them unpaired.
right.
So the charge is -3.
Right, but that's going to break down when we look at cations. So, I mean, it's kind of what you say is true for anions, but it won't work for cations. But we'll look at a cation in a minute, okay?
This time I tried to come up with some
Well,
pattern there, it's not gonna work.
you come up with good patterns, it's just that it's only a pattern that explains some things. That's one of the things I actually will talk about in chapter 11. When you explain things, sometimes it's easy enough to say, for instance, that, you know, it just gets, is there me or more people talking? Because I can't hear myself. Remember what? You just kind of cross on the periodic table?
Yeah, like if you're doing fluorine, it's past the 1s.
Yeah, we're getting to that in just one moment. We really are. So, finishing off fluorine. Notice that fluorine has normally a -1 charge because it needs one more electron. And then after fluorine is neon. I guess we'll do it in red, that's fine. So notice neon has all of its electrons filled in its shells that are occupied. What charge does neon have? Doesn't really react, right? We said that it's a noble gas. So one of the things that we're going to learn is that the reason noble gases don't interact or don't form bonds with other atoms is they've got enough electrons to fill their orbitals. They're completely happy just the way they are. They're like perfect people. They just are happy alone. Everyone else is always wanting to get rid of an electron or wanting to gain an electron or wanting to share an electron. But noble gases, they're just pretty happy to exist by themselves in their little island of perfection. So I'm going to go a little bit backwards and point out something. What am I writing the electron configurations for? What? Well, we're getting to that point. What's the same about hydrogen, lithium, and sodium? Yeah, they all are +1 cations. They all have the same outer shell configuration. Notice that if I take a look at it and I just look at the electrons in that outermost shell, that's 1s1. This one is 2s1. This is 3s1. So that's what we mean by the part that's the same. They all have one electron in an s orbital in their outermost shell. And then their other shells are all completely filled. And so what else do we recognize about lithium, sodium, hydrogen, lithium, and sodium? Where are they on the periodic table? First, yeah, they're in the same column. Oops. So one of the things that we've said about atoms in the same column is that they, or elements in the same column, is that they tend to react similar to each other, right? And for instance, they all have the same charges. So we know that all of the alkali metals, that's what hydrogen, lithium, and so on is going down that chart, all form +1 cations. Well, the reason they form +1 cations is they all have the same outer shell electron configuration. So quantum mechanics not only can explain the shape of the periodic table, it also explains what's the same about things in columns, or why it would be the same in columns. If only the electrons that are in the outermost orbitals can react, because they're the ones that are accessible to other elements or other atoms, then they're the only ones that really matter. They're the ones that we really need to count and keep track of. Does that kind of make sense? Sure, Owen.
For sodium, is it supposed to be 3s? 1s, 2s, 3s?
Yep.
Okay.
Because after the 2p orbital is the 3s orbital, right?
Okay.
So there's a lot of things that we're stringing together. You have to understand those energy level diagrams and the ordering of the orbitals. You kind of have to understand the Aufbau principles just a little bit. And then you have to kind of be okay with putting all the electrons in those orbitals and building those diagrams up. And remember, every one of these goes back to, you can actually just draw a picture. Unfortunately, you know, once the atoms get big enough, those pictures get complicated, you know. So it's pretty easy to draw hydrogen and lithium and realize that, you know, that's the electron that it wants to lose. Now, when you try to draw sodium, you know, you've got one orbital, two orbitals, you know, you've got your electrons in those. And then you've got your 3s orbital way out here. But then you also have to remember that you've got your 2p orbitals, so you've got to draw a bunch of those in there. And it quickly becomes horrible to try to draw a picture of an atom. It's so much easier to write 1s2, 2s2, 2p6, 3s1, and recognize that that is describing where the electrons are in the atom. And so that also explains why electrons don't pair up. So one last little mini topic. Valence shell electrons. So what we mean by valence shell is that it's the outermost orbitals. Or basically it's the orbitals with the highest quantum number. And because we're in this class, we're going to limit ourselves to s and p orbitals only. And the reason valence shell electrons are important is because they're the electrons capable of being gained or lost or shared in order to make a molecule. Or I guess technically ionic compound, if we want to be really specific and really complete in our definition. So even though, you know, for instance, if we pick an atom like iron that's got like 26 electrons or something, we don't really care about all 26 electrons. We only care about the electrons in its outermost orbitals. Or if we take a look at, you know, elements with higher numbers, we're not going to worry about the fact that they have 30 or 40 or 50 electrons. we're simply going to say how many electrons are in that outermost orbital, how many electrons are capable of making bonds. And we're even going to further restrict ourselves and say we're only going to look at s and p orbitals. We're going to talk occasionally about the d orbitals and say how they make things harder and more complicated and a little weird, but for the most part, we're going to stick with those s and p orbitals. And then the other thing that we're going to move forward looking at is called that octet rule. So if we take a look at s and p orbitals, we've got s2p6, well, that's 8 electrons. And so what the octet rule says is that all elements desire to have 8 electrons in their outer orbitals. Now, this is again ignoring the d orbitals. They make life complicated. And what that really makes them look like is it looks like a noble gas. So the driving force behind almost all the chemistry that we're doing is simply the number 8. We want to get to 8. We want to either share enough electrons so that everyone kind of feels like they have 8, or if we can gain and lose electrons to get 8 electrons, then we're going to do that. And so that's our octet rule. That's going to be probably responsible for like 95% of what we talk about in chapter 11, at least when we get to Lewis structures. So Aaron mentioned the periodic table, so let's go ahead and pull one of those up quick. Why is it so slow? But that's okay. Or not Aaron, sorry. Wait, no, it was. I don't know who I'm talking about. It was Aaron, actually. Maybe I'm just amazed that Aaron said something good. Okay, come on, computer. Don't be so slow. All I want is the periodic table. Is that too much to ask for in life? Just a periodic table. So, let's see. Can I write on here? Of course not. So one of the things that you should recognize is that you already know the charges for all the elements, right? And so if you look at the periodic table, if you understand the electron configuration for, say, hydrogen, then you kind of know the electron configuration for lithium and sodium. Same thing with fluorine. If you know fluorine's electron configuration in the outer shell, you know chlorines, bromines, and iodines, because they all tend to react the same. And then the other thing to recognize with these valence shell electrons is, for instance, you know, everything in the hydrogen column has how many electrons in the valence shell. Next column over, 2. Next column over, now we're skipping the D's, right? That has 3. Carbon has 4. Nitrogen has 5. Oxygen has 6. Fluorine has 7. Or neon has 8 in that column. So, can you guys all count to 8? Is there anyone missing more than 2 fingers? Because I don't care if you're missing 2 fingers, you can still count to 8, right? But if you're missing 3 fingers, then yes, chemistry is harder. But I think everyone's got all their fingers, so we're good. So if I take a look at it, for instance, if I draw, say, magnesium, let's just go ahead and pick that. So follow along on your periodic table, okay? Now, how many electrons does magnesium have? 12. So I'm just going to put, you know, a 12 next to it or someplace there. Now, if I'm going along the top of the periodic table, what are the first 2 elements? That's my 1s row, right? And there's 2 elements in it, right? Hydrogen and helium. And then I go down 1 row, so that means I have to go to a 2. And then I've got lithium and beryllium, so that's 2s2. And then I have those p blocks, so that's still in the second row, that's 2p, and there's 6 elements in those p blocks, right? And then I go down 1 row, and remember the s block is the furthest block on the left, and magnesium has how many electrons in that? 2. And so I'm done. So I can use the periodic table as a cheat for all of this. It's not like you have to memorize anything. Haley. Well, that's the 3rd row down, right? 1, 2, 3. So remember, the row that we're on in the periodic table is the first quantum number, right? Where we are on the periodic table, S, P, D, or F blocks, that tells me whether I'm putting in S, P, D, or F. And then the number that I'm putting there, like the 6s and the 2s, remember, that's just how many electrons we can fit in that orbital, or, you know, you can actually count the boxes if you have to. Someone pick another random element, something greater than, say, 50. Hafnium. Where the heck is that even on the periodic table? Oh, it's 72. Okay. This is why Owen's our favorite, because he picks good numbers. So let's look at hafnium. Just start counting on the top of the periodic table. It's going to be 1s2, 2s2, because we've gone through hydrogen, helium, lithium, and beryllium. Then I've got my 2p6. Notice the order is still the same in the beginning parts, right? Now I'm on my third row. I've got 3s2, 3p6, right? So what element am I on right now? Yeah, I'm going to start with potassium. That's on the fourth row, so that's 4s2, right? Now I have to go across the D block, but what do you remember about the D's? It lags by 1, right? Meaning that if I'm on the fourth row, that really is the third quantum number, or that is the 3D block. So the D's lag by 1 because of the way the energy levels mix. It's like you took the entire D block and just shifted it down one row. After the 3D10, what do I have then? I'm on my fourth row, 4p6. Now I'm on rubidium, right? So that's the fifth row down. So that's 5s2, 4d10. Remember, it lags. Now I'm on indium, right? 5p6. Then I'm now down one more row, so I'm on cesium. I'm going to 6s2. Now, notice on your periodic tables it's got that little star, and it's saying that really those f orbitals are down there, right? So the f orbitals are next, and remember they lag by 2, so that's 4f14. One of the reasons I picked, well, if you count 14 boxes, or if you remember the f orbitals, there's seven different types of f orbitals, meaning 7 different orientations. Each one can carry 2 electrons, so f's always have 14. And then we must be, let's see, that would put us on luteum, right? So that would be 5d, because remember they lag by 1. And then hafnium would be 5d2. Now, a good double check is to add up all the little exponents and make sure it adds up to 72. But I'm pretty sure I didn't make any mistakes, so I'm not going to double check it.
So how did you get the F's? So where are they supposed to go at?
Well, notice one of the reasons I picked your periodic tables is because I love this little part right here where notice that star. That's really saying that this is sandwiched in there. So remember, when we really think of the periodic table, we really have to go like this. You know, there's my S's, and then my D's, there's all my P's, and should go like this. Not to scale, okay? And then there's that little 2 empty blocks right here, right? What it's really saying is that the shape of the periodic table is like this. Here's my S's, here's my F's, but the F's are way down here in energy, and then it comes back up to my D's, and then my P's and stuff. So it really goes S, F, D, P, but instead we abstract the F's and stick them at the bottom of the chart, right? Or, I'll be honest, just count in numerical order. So notice that after 56, it goes to 71, and you should notice that there's something missing between 56 and 71. No, that's one of those weird things where you're just used to seeing these down here, right? And most periodic tables sometimes don't even leave that space in there. It took me forever to find a periodic table that left the space in there and made it explicit that that's where the f orbitals, or where those lanthanides and actinides really are. It's the best periodic table I've found, and technically I stole it, so such is life, but that's okay. They're not going to come after me. If they want to garnish my wages for copyright infringement, go for it. I'll just quit and work at McDonald's, and then they can't even make any money off me. And it'd probably be easier. I'd be fatter though because I'd eat so many fries.
Fast food's actually pretty hard.
What?
Fast food's actually pretty hard.
Oh, I know. It's a lot of work.
It's a lot of work for not much money.
Yes. Actually, I don't know. If I had my dream job, what would it be? Just being a millionaire. It's a job. It's effort to spend that much money. It has to be hard work. Those poor millionaires. So recognize that you can use the periodic table on all your tests, and you don't have to memorize everything if you understand how to use the periodic table. If you don't understand the periodic table, then you have to start memorizing more things.
And what is this? What were we doing?
These are electron configurations. And so the idea is that everything about this periodic table, everything that we know about charges, can be explained by that Schrodinger theory or the quantum mechanics theory, because it nicely falls all out of it. Now, it gets more complicated. For instance, we know that there are things that have variable charges, right? Like iron can have more than one charge. Well, it turns out that the d orbitals get a little messy, and that if you have a half-filled d orbital versus a full-filled d orbital and a couple other little things like that, it can change the energy levels enough. And so it turns out that they're so close in energy that it's pretty easy to form more than one charge on some things. Now, again, what did we say about d orbitals? We want to ignore them. So we're going to stick with the nice, easy S and P orbitals and realize that the d orbitals are there. They make things more complicated. They make things really a lot more complicated in the Chem 111 class, but since this is Chemistry 101, we're just going to be happy to ignore them. Makes my life easier too. Let's see. What that means is that homework, probably 10, I don't know, were we on C and D? Or basically due Friday. I think we're pretty much done with Chapter 10. We'll start in on Chapter 11
When do you think
on Friday.
Friday?
It probably won't be next week. It'll be the week after. So sometime, is that the week before Thanksgiving? Sometime in the week before Thanksgiving. Which is good because, remember, you forget everything over Thanksgiving. So it's better to remember all this stuff, take the test before Thanksgiving. Then you actually don't have to study so much chemistry. I've had tests where it was the week after Thanksgiving, and they're just a nightmare as far as I can tell. Everyone hates them.